This is part 3 of lecture 4.2 Relations. In this video, we will introduce the composition of two relations and give examples of proofs of statements involving this concept. Let R be a relation from a set A to a set B, and let S be a relation from B to another set C. The composite relation SR is the set consisting of all ordered pairs AC in the Cartesian product A cross C, such that for some object small b in the set C, the ordered pair AB is an element of R and the ordered pair BC is an element of S. In other words, small a is related to small c under SR if and only if for some small b in the set B, A is related to B under R and B is related to C under S. Suppose that these are the Venn diagrams illustrating the relations R and S. Under R, A1 is related to B1 and A2 is related to B2. Under S, B1 is related to C1 and B3 is related to C3. It follows from the definition of composition of relations that under SR, A1 is related to C1. A2 and A3 are not in the domain of SR, and C2 and C3 are not in the range of SR. The domain of SR is a subset of the domain of R. Indeed, for any object X, X is an element of the domain of SR if and only if, for some object Y, X is related to Y under SR. This is equivalent to the condition that for some object U, X is related to U under R and U is related to Y under S. This implies that there exist objects Y and U such that X is related to U under R, and there exist Y and U such that U is related to Y under S. This in turn implies that there exist objects Y and U such that X is related to U under R, which is equivalent to the statement for some object U, X is related to U under R. This is true if and only if X is an element of the domain of R. This shows that for any object X, if X is an element of the domain of SR, then X is an element of the domain of R. The range of SR is a subset of the range of S. The proof is similar to that of remark number 1 and is left as an exercise. The inverse of SR is R inverse S inverse. Indeed, for any objects X and Y, the ordered pair XY is an element of the inverse of SR if and only if YX is an element of SR. This holds if and only if for some object Z, Y is related to Z under R and Z is related to X under S. Equivalently, Z is related to X under S and Y is related to Z under R. And by the definition of inverse relation, X is related to Z under S inverse and Z is related to Y under R inverse. This is equivalent to the condition that XY is an element of R inverse S inverse. The operation of composition is associative. That is, for any relations R, S, and T, the composition of T and SR is equal to the composition of TS and R. Indeed, for any ordered pair AD, AD is an element of the composition of T and SR if and only if for some object C, A is related to C under SR and C is related to D under T. A is related to C under SR if and only if for some object B, A is related to B under R and B is related to C under S. Hence, the above is equivalent to the statement for some object C and some object B, A is related to B under R, and B is related to C under S, and C is related to D under T. It can be shown that this is equivalent to the statement there is an object B satisfying the conditions A is related to B under R, and for some object C, B is related to C under S, and C is related to D under T. The second statement in the disjunction is equivalent to the condition B is related to D under TS. Hence, the above is equivalent to the condition A is related to D under the composition of TS and R. Consider the relations R with elements 1A, 2B, and 3C, and the relation S with elements AX, AY, and CZ. Let us first get the composition XR. Observe that 1 is related to A under R, and A is related to X under S. Hence, the ordered pair 1X is an element of SR. A is also related to Y under S. Hence, the ordered pair 1Y is an element of SR. 2 is related to B under R, but B is not in the domain of S. Hence, SR does not contain any ordered pair with first coordinate 2. 3 is related to C under R, and C is related to Z under S. Hence, the ordered pair 3Z is an element of SR. Therefore, SR is the relation consisting of the ordered pairs 1X, 1Y, and 3Z. To get the composition RS, we begin with the elements of the relation S. A is related to X under S, but X is not in the domain of R. A is related to Y under S, but Y is not in the domain of R. So RS has no ordered pair whose first coordinate is A. C is related to Z under S, but Z is not in the domain of R. So RS has no ordered pair whose first coordinate is C. It follows that RS is the empty set. Consider the relation R, which consists of all ordered pairs xy of real numbers, such that y is equal to 2 raised to x, and the relation S, which consists of all ordered pairs xy of real numbers, such that x times y is equal to 1. The composite relation SR consists of all ordered pairs xy of real numbers, with the property that for some real number u, the ordered pair xu is an element of R, and the ordered pair uy is an element of S. That is, for some real number u, u is equal to 2 raised to x, and u times y is equal to 1. The condition u times y equals 1 is equivalent to y equals u raised to negative 1. Since u is equal to 2 raised to x, the predicate is equivalent to the condition y is equal to 2 raised to x raised to negative 1. Therefore, SR is equal to the set of all ordered pairs xy of real numbers, such that y is equal to 2 raised to negative x. On the other hand, RS consists of all ordered pairs xy of real numbers, with the property that for some real number u, xu is an element of S, and uy is an element of R. That is, for some real number u, u times x equals 1, and y equals 2 raised to u. The condition u times x equals 1 is equal to u is equal to x raised to negative 1. Hence, the predicate is equivalent to the condition y is equal to 2 raised to x raised to negative 1. Therefore, Rs is equal to the set of all ordered pairs xy of real numbers such that y is equal to 2 raised to 1 over x. Consider the claim for any relations R and S. If the range of R is a subset of the domain of S, then the domain of the composite relation SR is a subset of the domain of R. To prove this, assume that the range of R is a subset of the domain of S. We know from our remark at the start of this video that the domain of SR is a subset of the domain of R. So it remains for us to show that the domain of R is a subset of the domain of SR. Let X be an object and assume that X is an element of the domain of R. We need to show that X is an element of the domain of SR. That is, for some object Z, the ordered pair XZ is an element of SR. By the definition of domain, there is an ordered pair XY in the relation R for some object Y. Thus, by the definition of range, Y is an element of the range of R. Since the range of R is a subset of the domain of S, it follows from the definition of subset that Y is an element of the domain of S. So again, by the definition of domain, there is an ordered pair YZ in S for some object Z. Hence, XY is in R and YZ is in S. So by the definition of composition, XZ is in SR. Therefore, X is an element of the domain of SR, which shows that the domain of R is indeed a subset of the domain of SR. Together with the observation at the start of this proof, this implies that the domain of SR is equal to the domain of R. You have come to the end of part 3 of lecture 4.1. Before you proceed to part 4, you are strongly encouraged to do the exercises given at the end of these slides. Thank you for your attention.